right, so moving on with 19.3, looking at the symbols and terms of circuits. So we've been seeing these, but now let's get them into our notes. So if you see that in a circuit diagram, that would be a wire. This, where you've got two parallel plates, this is a capacitor. This would be a resistor. And sometimes these are light bulbs, because light bulbs are resistors. And then batteries, you've got a short plate, which is the negative plate, and then a long plate, which is the positive plate. So this is a battery. Sometimes you'll see the positive and negative sign in there, and sometimes you won't. So let's look at a couple really simple ways of setting up resistors. By the way, these are all called DC circuits with resistors. So direct current circuit with resistor. So if you have a circuit with resistors in series, so that means the current goes from R1 to R2 to R3 and then back around. So these resistors are in series, and they are ohmic, so we can use delta V is equal to IR. So let's think about how to treat this circuit in terms of our analysis. So we know the current's going to have to go from one to the other to the other. Is this just the same as having if they were all together, so R1, R2, R3, could we treat them as just one long resistor? Does it matter if there's some wire between them? Not really, because remember, yes, it's true that copper wire does have a little bit of resistance, but it's pretty negligible compared to this. So basically, it's just like it's one long resistor. So let's go ahead and derive that. So using energy conservation, or loop equations, and delta V is equal to Ri. So EMF minus R1I minus R2I minus R3I is equal to 0. EMF is equal to R1 plus R2 plus R3 times I. Let me introduce a new term, which is R eq or R equivalent, which is if this was just one giant resistor, what is the equivalent resistance? Which is equal to R1 plus R2 plus R3. And then if there's more in series, it would go on. And so we get the EMF is equal to R equivalent times I. All right, and this basically works because if we think back to what a resistor is, R is equal to L over sigma A. Oh my goodness. R is equal to L over sigma A. There we go. And conductivity is independent of current. It's just a property of the material. I mean, current can raise the temperature, and that might impact conductivity. And if you've got a steady state, I is the same. Everywhere. And by that we mean everywhere where you have current coming in, you have the same going out, and it's constant. It's not like a capacitance or a capacitor circuit. So, therefore, the sum of resistor potential drops is equal to potential rise of the battery, which is equal to EMF. Further, R is equal to L over sigma A, which is also rho over A. So if the resistors are of the same material, it's not always the case, but sometimes, and have same A, then you can look at length equivalent. So length equivalent would be L1 plus L2 plus L3 plus all the way to Ln. All right, and this is, of course, where A and conductivity are held constant. All right, so now let's look at parallel resistors. So for this, you have your current coming around I, and then so the current's going to split to go down these different paths. I'm going to go ahead and cross out that one there on the end. And you can see that these resistors are in parallel. So they're not all going to get the same amount of current because the current's going to split into the different branches. So using I is equal to delta V over R, and again, we're assuming ohmic resistors, and you can basically assume this every time unless you're given indicator otherwise. So, and to really get indicator otherwise, in a class like this, it would be extremely explicit, but in the real world, you would just you would be doing a little bit more advanced circuit analysis than what we do here. Okay, so we can say that I minus EMF over R1 because there's going to be a drop there, minus EMF over R2 minus EMF over R3 is equal to 0. And therefore, we can factor out what is the same. So I is equal to 1 over R1 plus 1 over R2 plus 1 over R3 times EMF. And so I, for parallel resistors, is equal to EMF over R equivalent. And in this case, our R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3 dot 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 to however many resistors you have in parallel. All right, and we could also think about this, that if the resistors are made of the same material, and have the same length, you could think about it as though their cross-sectional area was just being combined into one big one. So then you'd have REQ is equal to A1 plus A2 plus A3 dot 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 to AN, however many you have in parallel. Okay, so let's do an example. And we're going to look at a circuit that has both parallel and perpendicular, both parallel and series resistors in it. So we want to calculate REQ of a series parallel circuit. So, and when you see this, it just means that there's a circuit coming in. So I'm just going to draw a little piece of it and not draw the whole thing, just to get you familiar if you see that as well. So we've got some circuit, we've got current coming in, and it goes through this resistor, it branches into two branches, hits those two resistors, and then keeps flowing and goes around. R1 is equal to 8.0 ohms, R2 is equal to 12 ohms, and R3 is equal to 14 ohms. And of course, these are ohmic materials. We've been given no indication otherwise. All right, so to attack this problem, we're going to need to break it up into parts. So the first thing we want to do, at this point, it would be, can't really do a series calculation for resistance because it would go from here and then we don't know what to add there. So we want to start off by doing the resistance of the parallel section. So of the parallel circuit. And we will call this R4. So 1 over R4 will be equal to 1 over R2 plus 1 over R3. This is equal to 12, equal to 1 over 12 ohms plus 1 over 14 ohms, which is equal to 13 over 84 ohms. And R4, we would then need to take the inverse to get that, is equal to 84 ohms over 13, which is equal to 16.5 ohms. All right, so now that we have the resistance for this section, we could essentially treat this as though we have two resistors in series. So we have R1 is equal to 8.0 ohms and R4, which is equal to 6.5 ohms. So that is our new problem as we head towards equivalent resistance. So our equivalent for this circuit is equal to 8.0 ohms plus 6.5 ohms, which is equal to 14.5 ohms. And so we could then just basically, we've reached the end. We now have some resistance R5, which is equal to our equivalent, 14.5 ohms. And the reason I've listed as R5 is I know that there's more to this problem coming. Okay, so now we're going to apply 20 volts across the network and find the voltage across and the current through each resistor. And we'll work backwards, starting with total resistance. So let's work backwards. So we have I is equal to delta V over R. which is equal to 20 volts over 14.5 ohms, which is equal to 1.4 amps. All right, this is very useful because we know that this is a steady state circuit, so it will always at any junction have 1.4 amps of charge flowing through. So at R1, which if we follow our picture is right here, then delta V1 is equal to I times R1, which is equal to 1.4 amps times 8.0 ohms, is equal to 11 volts. And then at R4, so that would be that resistor that is the combination of the two parallel resistors. And you have delta V4 is equal to IR4, which is equal to 1.4 amps times 6.5 ohms is equal to 9.1 volts. Now, this is going to be the important one for what comes to follow. So 1.4 amps divides R2 and R3, and that delta V, 9.1 volts, will stay the same over that total section. So then you get I2 is equal to 9.1 volts over 12 ohms, which is equal to 0.76 amps. And I3 is equal to 9.1 volts, which is equal to 14 ohms, which is equal to 0.65 amps. So in this case, in the section with the lower resistance, then it got more current, and the one with higher resistance got a little bit less, which makes sense. So that is how you approach doing a circuit analysis for a series parallel circuit.